Let's start with looking at operational amplifiers, or op-amps. Many useful signal conditioning circuits can be built using op-amps. Some of the most common are presented in the pages that follow, starting with the voltage follower circuit. The voltage follower, which is a very useful circuit, can boost the current of a signal without increasing the voltage. It can transform a high impedance signal, which is easily loaded down, into a robust low impedance signal. The figure shows a voltage follower circuit. It has a voltage gain of 1 with a high input resistance R in and a low output resistance R out. Its operation can be explained as follows. We start with the basic op-amp equation. V out equals the gain times the difference of the voltage, V2 minus V1. In the circuit, V out is connected to V1. Thus, V out equals V1, and substituting V out and expanding, V out equals A V2 minus A V out. Solving for V out, we get V out as being equal to A times V2 over 1 plus A. And since A is in the order of 100,000, and 100,000 over 100,001 is basically 1, we get V out is equal to V2. We see that the output voltage V out equals the input voltage, meaning the overall gain is 1. We also notice that the actual input signal goes directly into the non-inverting input, so it draws essentially no current. A more intuitive way to explain a voltage follower circuit is as follows. The input V2 is virtually the same voltage as V1. We know that from our assumption 1 we just looked at. V1 is connected to V out, so it's as if V2 were connected to V out, hence the gain of 1. The voltage follower is a simple and very useful circuit. Consider the situation shown in figure A. In this case, a high impedance sensor, 10 kilo ohms, is connected directly to a controller with a 1 kilo ohm input resistance. The sensor generates 5 volts internally, but this is reduced by the voltage drop across the 10 kilo ohm internal resistance. By redrawing the circuit in figure B, we see that these two resistors form a voltage divider. The actual input voltage to the controller can be calculated as follows from the voltage divider rule, where Vn equals 1 kilo ohm times 5 volts over the sum of 1 kilo ohm plus the 10 kilo ohms, or equaling 0.45 volts. This shows that only 0.45 volts of the 5 volt signal makes it to the controller. Let's go through the maths by yourself to make sure you're happy with that. The previous slide showed that only 0.45 volts of the 5 volt signal makes it to the controller, less than 10%. We could amplify the signal to the controller to make up for the attenuation, but that would amplify the noise as well as the signal. A better solution is to insert a voltage follower near the sensor, as shown in figure C. Because the op-amp draws no signal current, there is no voltage drop across the 10 kilo ohm resistor, and the full 5 volts enters the voltage follower and appears at its output. The 1 kilo ohm input resistance of the controller is so much higher than the output resistance of the op-amp that almost all of the 5 volts will appear across the controller terminals. The inverting amplifier is probably the most common op-amp configuration. The circuit shown requires just 2 resistors, labeled Ri for our input and Rf for the feedback resistance. Ri is the input resistor, Rf is the feedback resistor that feeds part of the output signal back to the input. This is an inverting amplifier because the input signal goes to the inverting input, which means that the output is out of phase with the input. The voltage gain is determined by the resistor values. An explanation of how the inverting amp works is as follows. First, if the op-amp input draws no current, then all the signal current In must go through RF. There is nowhere else for it to go. Hence, In equals IF. By assumption, V1 and V2 are virtually the same voltage, and V2 is grounded. Thus, V1 is at virtual ground. If V1 is almost at ground, then the entire input signal voltage, Vin, is dropped across Ri. From Ohm's law, In equals Vin over Ri. As already noted, virtually all of In goes through the feedback resistor Rf. The voltage across Rf is the difference between the virtual ground and Vout. Thus we can rewrite Ohm's law for Rf in that In is the same as If, which is equal to 0 minus Vout divided by Rf. Combining the two equations, Vin divided by Ri equals 0 minus Vout over Rf, and solving for Vout and rearranging gives us Vout is equal to minus Vin times Rf divided by Ri, or Vout over Vin equals minus Rf over Ri. However, we know that Vout over Vin is the voltage gain. So AV, the voltage gain, AV, is minus Rf over Ri, where AV is the voltage gain of the inverting amp. This result shows us that the voltage gain of the inverting amp is simply the ratio of the two resistors Rf and Ri. The minus sign reminds us that the output is inverted. The gain derived, AV, is called the closed loop gain and is always lower than the open loop gain of the op-amp itself. Another important point is that the input impedance for the entire inverting amp is approximately Ri. It's not infinite as you might think. The right end of Ri is at virtual ground. Therefore, the entire input voltage Vin is dropped across Ri. An inverting amp is to have a gain of 10. The signal source is a sensor with an output impedance of 1 kilo ohms. Draw a circuit diagram of the completed amplifier. Hint: your op-amp input resistance should be at least 10 times higher, if possible, than the signal source impedance to ensure maximum voltage transfer. We can draw the sensor first as a voltage source with a 1 kilo ohm resistance. Next, we draw the inverting op-amp circuit, and we select Ri equals 10 kilo ohms to make the op-amp input resistance 10 times the input source impedance. Next, we rearrange the inverting amp equation to solve for Rf, where Rf equals minus ARI. Bring some numbers in there. We get minus 10 times 10 kilo ohms, or 100 kilo ohms. Many situations call for an amplifier that does not invert the output. For example, the output of a temperature sensor might be such that as the temperature goes up, the voltage goes up. If this is the same relationship that the controller wants, we don't want the amplifier to invert it. The circuit for the non-inverting amplifier is shown. It is similar to the inverting amp, except the input signal Vin now goes directly to the non-inverting input, and Ri is grounded. Notice that the non-inverting amp has an almost infinite input resistance, Ri, because Vn connects only to the op-amp input. An explanation of how the non-inverting circuit works is as follows. If V1 is virtually the same as V2, then the voltage input Vin appears across Ri. Applying Ohm's law to Ri, we can calculate In. So In is equal to Vin minus 0 over Ri. The current in RF can also be calculated using Ohm's law. We know the voltage across RF is the difference between Vin and Vout. Therefore, If equals Vout minus Vin over RF. Because no current enters the inverting input of the op-amp, all current in RF must go into Ri. So In equals If. Combining these three equations and solving for Vout gives us Vout over Vin equals Rf over Ri plus 1. We note that Vout over Vin is the voltage gain, so the resulting equation for the gain of a non-inverting amp is AV equals Rf over Ri plus 1. Again, perhaps pause the video and check you're happy with that math. An example of a non-inverting amplifier. Design the circuit diagram of a non-inverting amp with a gain of 20. Hint, the basis for selecting both Ri and Rf is that the current in these external resistors should be much larger than the small current that actually enters the op-amp. Recall that the op-amp equation was based on the assumption that no current enters the op-amp. Therefore, both Ri and Rf should be at least 10 times smaller than the op-amp resistance of 1 megaohm. In this case, no more than 100 kiloohms if possible. Using the non-inverting amp equation just developed and putting in a gain of 20, we get AV is equal to 20 equals Rf over Ri plus 1. Rearranging gives us Rf over Ri equals 19, or Rf equals 19 times Ri. Now select Ri to be an appropriate value and solve for Rf. If we select Ri to be 2 kiloohms, then Rf equals 19 times 2 equals 38 kiloohms. Note the equation is a ratio and there are many options that will work. 1 and 19, 3 and 57. The final choice of resistors will depend on a number of factors that you will pick up along your training, and you shouldn't worry about it too much now. The summing amplifier. The summing amplifier has an output voltage that is the sum of any number of input voltages. That is, Vout equals VA plus VB plus VC. As you can see from the diagram, those are the input voltages. Each input signal goes through a separate resistor that keeps it isolated from the others. The inverting input is used, so the output will be inverted. Pay attention to the sign of the voltage. An explanation of how the summing amplifier works. Because the op-amp input draws no current, all individual input currents must combine and go through the feedback resistor RF. So IF equals IA plus IB plus IC. Note that V2 is grounded, so V1 is at virtual ground. Therefore, the voltage across each of the four resistors is simply VA, VB, VC, and Vout. Applying Ohm's law to express the current through each resistor, we can rewrite the equation as follows. 0 minus Vout over RF equals VA over RA plus VB over RB plus VC over RC. Solving for Vout, Vout is equal to the negative of RF over RA times VA plus RF over RB times VB plus RF over RC times VC. In other words, the output voltage equals the sum of the products of the input voltages and their respective gains. Also, the input impedance of each input equals the value of the respective input resistor, RA, RB, etc. If we make RA equal to RB equal to RC and we call it RI, the output of the summing amplifier simplifies to Vout equals the negative of RF over RI times the sum of VA, VB, and VC, where RI is the value of all input resistors, which we've made the same. An instrumentation amplifier is a differential amp that has its inputs buffered with voltage followers, as shown. Voltage follower circuits on their inputs perform three desirable functions. Firstly, they increase the input resistance so that the source, such as a sensor, will never be loaded down. Secondly, they make both input resistances equal. And thirdly, they isolate the gain-defining resistors, RF, RI, etc., from the signal source. This last quality means that instrumentation amps can be pre-built and have a specific gain. Op-amp circuits can be designed to integrate or differentiate an incoming waveform. These special-purpose circuits are likely to be found only inside an analog controller. The integrator circuit works by converting the input voltage Vin into a constant current source that forces the capacitor C to charge at a linear rate, thus building up the voltage across C. The feedback element is a capacitor. The integrator gives an output voltage Vout that is proportional to the total area under a curve traced out by the input voltage waveform, the horizontal axis being time. The integrator circuit works by converting Vin in a constant current source that forces the capacitor C to charge at a linear rate, thus building up the voltage across C. The integrator concept can be explained by the sample waveform shown, which assumes numerical values of R times C of unity, or RC equals 1. Notice that the integrator input Vin rises from 0 to 1 volt in the first 10 seconds. The triangular area under that portion of the curve from A to B is 5 volts, 5 volt seconds. So the output Vout of the integrator goes from 0 to minus 5 volts during the same time. In other words, the output voltage ends up being the same magnitude as the area under the curve, in this case, 5. The minus sign appears because it is an inverting amp. From time B to C, Vin remains at 1 volt. So the new area added is 10 volt seconds. Consequently, the magnitude of Vout increases by 10 to become minus 15 volts at time C. Then Vin returns to 0 volts. Because no new area is added between C and D, Vout remains at minus 15 volts. Integrators can be useful because they keep a record of what has gone on before. The simple integrator circuit shown is not practical because any offset voltage, and there's always some, will eventually cause the output to build up and saturate at the power supply voltage. One solution is to put a resistor RF across the capacitor to draw some DC feedback. If the value of RF is at least 10 times greater than R, the circuit performance will usually not be adversely affected. The differentiator. The differentiator gives an output voltage that is proportional to the rate of change or the slope of the input voltage. Notice the voltage is inverted. The differentiator concept is as illustrated by looking at a changing input voltage signal. Once again, we define RC to be 1 to keep the math easy. From time A to B, the input voltage Vn is 0 volts. And because it's not changing, the output voltage Vout is 0 volts. Again, the differentiator shows a signal proportional to the change of the input. During the time period B to C, Vin increases at a constant rate of 1 volt per second. So the Vout curve reflects this by staying at a constant negative 1 volts. It is negative because the inverting input is used. From time C to D, the slope of V increases at 2 volts per second, so Vout jumps to minus 2 volts. After time D, V in stays at 3 volts, and because it's not changing, V out is 0. Differentiators can tell us how fast a variable is changing. In practice, however, they suffer from the problem that even a small amount of noise in the input will be accentuated, giving a very noisy output. We are not finished with the op-amp circuits, but I'm sure you guys could do with a break. We will pick up the op-amp in C02 and hopefully it will all start to gel.